We measure radioactivity in what's called half-lives. You see, the atoms in radioactive material spontaneously just break apart or decay. Now, we can't tell when an individual atom will decay, but we can tell when a fraction of them will. So a half-life is the amount of time it takes for half the atoms in a piece of radioactive material to break apart. Now, plutonium has a half-life of 24,000 years. So let's say this red water is the plutonium in a spent nuclear fuel rod fresh from the reactor. Well, after one half-life, 24,000 years, diluting this water by half, it looks like this. After two half-lives, 48,000 years, it would look like this. After 10 half-lives, 240,000 years, the water starts to look pretty clear. Now, plutonium is notorious. It's especially radioactive. It's 20 million times more radioactive than uranium dug from a mine. You see, we're not talking about potato salad left out in the sun. We're talking about plutonium.
We're going to talk about nuclear half-life, and then we're going to do some practice math problems on this stuff. So, nuclear half-life tells us how long it takes for nuclear processes to occur. So a nuclear process is one where the number of protons and neutrons in an atom's nucleus, where the number of those protons and neutrons change. Here is an example of a nuclear process. So here we have thorium-234, and it is undergoing beta decay, which means that one of its neutrons turns into a proton. So it originally had 90 protons, and then it gets 91 protons. But here's the thing. The number of protons an atom has determines what kind of an element it is. So when thorium, which had 90 protons, ends up getting 91 protons, it changes into a different element. What used to be an atom of thorium now turns into an atom of Pa, proactinium. Okay, so this is a decay process for thorium turning into proactinium. Now, we said nuclear half-life tells us about how long it takes for these sort of processes to occur. How long does it take for this to happen, for thorium to turn into proactinium? Well, let's talk about this. Let's say we start with 80 grams of thorium. If 24 days go by, at the end of those 24 days, I'm going to be left with 40 grams of thorium. The other 40 grams of thorium have turned into proactinium. Okay, so I'm only left with 40. Now, after another 24 days, there's only 20 grams of thorium left. And after another 24 days, there's only 10 grams of thorium left. All the rest has turned into proactinium. So here's the thing. Every 24 days, the amount of thorium that we have gets cut in half because the other half becomes proactinium. So we'd say that for this process, for this reaction, the half-life is 24 days. So half-life is the time that it takes for 1/2 of a certain amount of thorium to decay, to turn into proactinium, to disappear. Okay? So 24 days to go from 80 to 40, the amount we have gets cut in half. 24 days to go from 40 to 20, cut in half again. 24 days to go from 20 to 10, gets cut in half again. And remember, it's not, I'm saying disappearing, but it's not that it disappears. It's that it's just not thorium anymore. It's becoming proactinium. But so when I say disappear, that's what I mean. Sometimes I think it's easier to think about that. Okay, so anyway, we say that half-life, the time required for half of a sample to decay. And we often abbreviate half-life with lowercase t with this 1/2. So I can write here that the t 1/2 for this is 24 days. Okay? Maybe you're more of a visual person. So let's look at a quick graph of what's going on here. Okay. Let's imagine that this is a graph of thorium turning into proactinium. Here's the amount of thorium that we start with. And then after one half-life, we have half of it. And then after another half-life, we have half of this. And then after another half-life, we have half of this, and so on. Okay? Now, if this is showing us thorium going to proactinium, each of these bars would be separated by 24 days. That would be the amount of time between them. Now, all nuclear reactions, all these different decay processes, have different half-lives, okay, for different amounts of time. For example, and I should say that these amounts of time vary widely. So for example, uranium-238 here undergoes alpha decay to make thorium-234. And the half-life for this reaction is 4.5 billion years, which means that it would take 4.5 billion years for half of a sample of uranium-238 to turn into thorium. Okay, but then on the other hand, polonium-218 undergoes alpha decay to make lead-214, and the half-life of this process is only 3 minutes. So that means that if you were in the lab studying polonium-218 and you had to get up and run to the bathroom for 3 minutes, by the time you came back, half of the polonium you had in your sample would have disappeared. It would have turned into lead. Okay? So if this were a graph for uranium's decay instead of thorium, the difference between each one of these bars would be 4.5 billion years would be the amount of time between each half-life. And if this were polonium, it would be 3 minutes to go from here to here and 3 minutes to go from here to here. So that is half-life, the time required for half of a sample to decay, to turn into something else, to, as I keep saying, to disappear. Okay, so that's a background on half-life. Now let's do some calculations for half-life.